All right, looks like pretty much everyone who, well, not quite everyone, but people on Zoom, type something into the chat to let me know that you're here if you haven't done so already. There's at least one of you that has not. Roll sheet for people. Oh, well, it's because you're physically. Yep. All right. So today we are going to be talking about differential amplification. Just a moment. Oops, I had not unmuted myself. So today we're going to be talking about differential amplification. So let's start with a simple introduction to the topic. And the most obvious question with regards to differential amplifiers or differential amplification might be where to use them. So up to this point, all of the transistor amplifiers that we have looked at have been single-ended, meaning that they have a single input and a single output. So we might consider that to be something like this. We have an amplifier with some particular voltage gain. We apply let's just say some signal. I'm going to call this the signal. And for the sake of argument, let's say that it's roughly sinusoidal, meaning that the total signal being seen by the amplifier's input terminal is sinusoidal, and the signal seen at the output, the out, is just a larger version of that sinusoidal signal. So that's how a simple single-ended amplifier works. Now, obviously, we can have things like inversion and all that kind of good stuff. So for example, with common source or common emitter amplifiers, we would expect for an input sinusoid, we would get an output negative sinusoid because of the inversion characteristic of that amplifier. But we're not worrying too much about phase shift at this point. While a single-ended amplifier is useful for a wide range of applications, one of its principal drawbacks is that if we had any coupling of noise or spurious signals to our input, that signal would also be amplified. So another way to think about this is if this were part of a larger integrated circuit and there were, say, a clock signal being run to a digital circuit nearby, there might be some sort of coupling such that we would see noise or distortion on our input signal. And so what I mean by that is, let's take our same single-ended amplifier. And let's say that we have our voltage V signal as before, and we're going to add to that some random noise. I'm going to call this guy V noise, and here is my output V out. my signal is again my simple sinusoid, then I'm going to see that show up at the input terminal, but I'm also going to see random noise show up at the input terminal. And when I combine them together, I'm going to get a noisy output sinusoid. I mixed red and blue to make purple, trying to make things work there. So we have to come up with some method to suppress this noise. There are three different kind of schools of thought on this. So let's consider a real world problem with noise. Let's say that Nicole is sitting there trying to listen to my lecture. And as per usual, Mr. Albert is sitting here being a bit of a chatty Cathy and creating a bunch of noise, okay? So there's my vocal signal that's trying to reach Nicole, and then there's a noisy signal that's also reaching Nicole, and she's hearing the conglomeration of those two things. Her options are threefold. She can reduce her sensitivity to the noise. She can decrease the noise coupling, or she can, I'm trying to think of the best way to put this, decrease the noise level overall. So to decrease the noise level overall, she could say, hey, Chris, shut up. That would be one way to get rid of the noise in her system. Another way would be for her to just say, well, I don't really care all that much. That would be decreasing her sensitivity to the noise. And for decoupling, she could just maybe move further, something like that, so that she didn't hear the noise that Chris was generating so much, but she might also not be able to hear me as much either. So those are the three different ways that we can really kind of look at this. In a circuits-based approach, we're really kind of limited. Those are still the three different ways that we can do things, but we often see that we have limitations or constraints. So for instance, if we wanted to decrease the coupling, which is probably the most obvious thing, we might have to move different portions of our circuit physically away from each other, which is going to increase their size, increase their footprint, and increase the overall chip cost and things like that. So while that's probably the best way to do it, it's also usually the most expensive way. Decreasing the sensitivity to the noise and all that kind of stuff would involve building a more robust system, which is also going to be prohibitively expensive, and simply ignoring the noise is going to lead us to have untenable signal to noise ratios, meaning that there's going to be instances where we can't actually differentiate our signal from the noise surrounding. So what we are going to talk about today is differential amplification, which is primarily used as a noise reduction technology. And so how differential amplification works is if we apply, let's say that we have a double-ended amplifier. So let's introduce something like that real quick, okay? Here's our single-ended amplifier. Let's say that we instead have a double-ended or differential amplifier. So that would be something that looks like this. We're going to have two input terminals, the N1 and the N2. And typically one of those input terminals is non-inverting and the other one is inverting. And that's pretty critical for what's called common mode rejection, which we'll talk about in much greater detail later on. But we might also see that we have two outputs. The out one and V out 2. So this would be a fully differential amplifier, right? We have 2 input signals, we get 2 output signals. But what we can do to eliminate noise is use one of our output signals as a reference to our other output. So for example, I could do something like this, where I'm using V out 2 as a reference for V out 1. So if I have such an application and I configure my circuit like so, where I have my signal applied here, and my noise applied here. So on my non-inverting terminal, I'm going to see my signal and some noise. But on my inverting terminal, I only see that exact same noise. And what I get at my output is the difference, which looks like simply a scaled version of my output signal without any noise. So we are amplifying the noise for sure, but we're also subtracting out that exact same amplified noise as well, leaving us with a relatively undistorted output signal. So that brings us to what we're going to call differential and common mode signals. All right. So for any differential amplifier, we can break down the inputs and outputs into common mode and differential mode signals. So a differential mode signal is simply the difference of the 2 input or output signals. So for us, that would mean that we would have some differential input signal, which I'm going to call VID, is simply VN1 minus VN2. And we can have a differential output signal, VOD, which we'll define to be Vout1 minus Vout2. A common mode signal is simply the average value of the input or output signals. So we can think of it as whatever signal winds up appearing at both terminals. The reason why I prefer to look at it as an average value is because we may not always actually apply an input to our second input terminal. We might be referencing something with respect to ground or something like that, or a specific DC voltage or something. So we could say that VI common mode is VN1 plus VN2 over 2, and V out common mode is V out 1 plus V out 2 over 2. And we can actually take these two representations and deconstruct any input signals into a common mode portion and a differential mode portion. And so what I mean by that, and I'm going to do just this in some circuit analysis later on, VN1, I can say, is my input common mode signal plus 1/2 of my input differential signal. So just to make sure I'm not telling tales out of school here, this would be, let's see, VN1 plus VN2 over 2 plus VN1 minus VN2 over 2 is exactly equal to VN1, right? So I'm just decomposing it into a common mode and differential mode signal. And I can do the exact same thing and say that VN2 is simply VN common mode minus VID, the input differential signal, over 2. Sure. So let's work a very trivial example problem, right? Let's say that we have a differential amplifier has a voltage gain of AV is equal to 5 and is used to amplify following input signals. VN1 is equal to 1 plus 0.5 cosine omega naught t volts, and VN2 is equal to 1 minus 0.5 cosine omega naught t volts. I want us to figure out what the input common mode signal is, the input differential mode signal, the output common mode signal, and the output differential mode signal. It's going to be real trivial, right? So we could say the input differential mode signal, VID, again, is just going to be VN1 minus VN2. So what should I observe? One cosine omega naught t, right? Okay. So we would say that we have an input voltage swing of twice the amplitude of our original sinusoid, right? Because we are subtracting away some portion and these two signals are completely out of phase with each other, our input signal is actually getting, or our differential input signal is actually experiencing a boost or an enhancement, right? Because they're both 180 degrees out of phase, the constructive interference between those two is going to make our amplifier see a differential signal that's twice as large as the AC portion of either of our inputs. Our common mode is VN1 plus VN2 divided by 2, or the average value of these guys. So what should it be? Just 1, right? 1 volt. For our output, we're going to have AV times VN1 minus VN2. So if we had 1 cosine, we should now have 5 cosine omega naught t volts. And for our differential, excuse me, for common mode, VOCM, we're going to have AV times VN1 plus VN2 divided by 2. So we should see a DC value of 5, or an average value of 5. Okay, so this, again, real trivial. Just want you guys to understand exactly what's going on, and particularly the concept of being able to boost signals with this. So this was boring. Let's talk about something a little bit more pertinent and relevant to what you guys have done. So all of you guys are in the 339 lab, right? What'd you do last week? Made rectifiers, right? So let's say that we had the following circuit. Give myself a little bit more room. Call this guy C1. So we got a simple full wave rectifier here. I believe you guys were converting, well, you weren't converting exactly this, but I'm just going to do this because I'm lazy. 120 volts RMS at 60 hertz. Your transformer, I guess this is actually pretty true. You had it plugged into the wall, your transformer stepped it down to some value, and then you were amplifying a signal, right? Or you were measuring the ripple. So you saw some power supply ripple voltage. In this case, we're going to be using this guy to drive a Bjt amplifier. Call this guy RC. And up here, we have VCC, which is going to have some DC value plus some ripple. Missing one thing here. Let's call this guy CN. And just let's say that connected to this node, there is a biasing resistor network that establishes the DC operating point of the base, right? What should we expect to see at our output if we applied a simple sinusoid in a best case scenario with a very, very small ripple voltage, a negligible ripple voltage? Our output signal would be nearly perfectly sinusoidal, right? But if our ripple voltage is large, we are going to expect to see that our output voltage is going to be sinusoidal, a sinusoidal signal superimposed on top of a AC ripple signal as well. So we're going to see a lot of distortion. How we could fix that would be converting this single-ended BJT amplifier into a differential BJT amplifier. Anybody have any thoughts on how we might do that? How can we make the same ripple signal show up elsewhere so that we can cancel it out? That's the question I'm asking here. Anybody got any thoughts? So we're going to accomplish this as follows. Go away, keyboard. Come back, regular screen. Q1, Q2, let's call this RC1, and let's call this guy RC2. So effectively, all we've done is connected an identical, or well, right now we have connected another common emitter amplifier in parallel to this guy's. If we want it to completely cancel out the noise seen caused by our ripple, we need to make sure that RC1 is exactly equal to RC2 and transistor Q1 is identical to transistor Q2. This is the basis for the transistor-based differential amplifier. Now, we are going to make one more change to this to get into the real practical amplifiers that are in use. And that change is going to be adding a current source into this system, okay? So let me talk a little bit about why we're going to add a current source. For this particular system, as our input signal gets larger, our collector current should also get larger, right? When for small signals, if this gets larger, then we have some signal here where VBE is getting slightly larger due to our small signal input, which is causing more current to flow here, but the amount of current flowing here is fixed. And what we are going to observe is what's called common mode gain, meaning we are still going to be amplifying some small portion of our ripple current, or our ripple signal, because we haven't made a further restriction, okay? So, now let's talk about the Bjt differential pair, which solves this. And today we're going to be focusing pretty much entirely on only the large signal model, which we haven't looked at the large signal model for an amplifier in quite some time, but this guy behaves a little oddly, so it's necessary. So our Bjt differential pair is going to look something like this. We have some resistor RC. Here's transistor Q1. Here's V out 1. Here's IC1. Here's IE1. Here's VN1. We mirror it over here. Or, yeah, I guess I can say that without it being too confusing, I hope. Here's V out 2. Here's VCC. Here's IC2. Here's IE2. Here's VN2. So far we have the exact same thing that we had a moment ago. Now here is the big change. We apply some current source, and in this case it's ideal, to the point where our two transistors are tied together. So the common emitters of both of these guys, right? So let's talk about what this guy does specifically to a common mode signal, all right? So if a common mode signal is applied to the inputs, what happens to IC1, IC2, and VOD, our output differential voltage, all right? So let's just say, for the sake of argument, that we have a voltage of 1 volt applied at the input VN1, and that same voltage of 1 volt is applied at the input of VN2, okay? What can we say about the base emitter voltages of both of the transistors? Thoughts? All right, so to be clear, 1 volt, 1 volt. This is the base. This is the emitter. This is the base. This is the emitter for transistor 2, right? My base emitter voltage, what is their relationship between each other? They have to be identical, right? We're applying the exact same signal to both of the inputs. So what does that mean is happening to currents IC1 and IC2? If the base emitter voltages for the two transistors are identical, and the transistors are identical, and the resistors RC1 and RC2 are identical, what does that tell me about the collector currents? They have to be the exact same thing. So IC1 has to be exactly equal to IC2, but we know also that IE1 and IE2 are identical, because if the collector currents are the same, then the emitter currents are the same, and IE1 and IE2 have to add together to be IEE. So what that means is that IC1 will be equal to IC2, which will be equal to alpha times IEE over 2, where, just as a quick refresher, alpha is beta over beta plus 1. So I'm just taking into account the fact that my emitter current is a little bit larger than my collector currents. All right. What does that mean with respect to our differential output voltage? So we have the exact same current flowing through both of those resistors RC. So Vout1 should be VCC minus ICRC. Vout2 should be VCC minus ICRC. And the difference of those output voltages must continue to be 0, right? So we have complete common mode rejection. All of our, or none of our common mode signal is amplified in any way, shape, or form. It is all entirely attenuated, okay? So let me write this down. Vout1, VCC minus ICRC. Vout2 is equal to VCC minus ICRC. Putting these guys together, VOD is equal to 0, which means all common mode signals are attenuated. Now, what's interesting about this guy, okay? What if we changed our common mode signal from 1 volt to 1.5 volts? What's going to happen? Can IC1 or IC2 change? No, right? It should not matter what our common mode voltage is. There is a constraint on that we'll talk about momentarily. But if we apply only a common mode signal, we know that Vout1 and Vout2 have to be identical. We know that IC1 and IC2 have to be roughly 1/2 of IEE. So if we are changing the base emitter voltage, but our collector current isn't going up, how is that possible? Let's start there. This is, I guess, more obvious on a ideal current source than anything else. Okay. So if VBE is increasing, but the collector current has to stay the same, what it's doing is it's shifting the voltage here at node X up and down to accommodate the changes in VBE, right? If we apply a larger common mode signal, or with respect to ground, but we're still forcing the exact same current to flow through both of the resistors, then the potential at that node X must change to make VBE match, be a constant value as the input signals go up and down with respect to ground, okay? Because there is a constant ideal current source here, if we applied a negative voltage at our inputs, we would still expect to see Vout is equal to 0, and just this potential at node X would be negative to accommodate that particular amount of current flowing through each of those guys. Now there is one fairly significant restriction here. We actually can't let our common mode voltage get too large. And so what I mean by that is, if we let our common mode voltage get too large, we will actually force these guys into saturation, right? So, here. Our restriction on this all signals being attenuated is true only if our common mode voltage, VCM, is less than or equal to VCC minus 1/2 alpha IEE RC. If our common mode voltage is greater than this, we're actually forcing the transistors into out of forward active region operation and into saturation region operation, where things get hinky and we don't want to do that. All right, so we got our common mode rejection down. Now let's consider what happens if VN1 is much larger than VN2, so that we're still dealing with a large signal analysis here. What happens to IC1, IC2, and our differential voltage VOD? All right. So I think in the textbook, they describe this condition effectively as like if we left this guy at +1 volts, but we moved this guy to +2 volts. So in this condition, our differential voltage VN1 minus VN2 is now positive, right? And so let's start with something real easy. We weren't specifically asked about it, but VID is greater than 0. This will be useful to us later on, right? Since VN1 is greater than VN2, that means VBE1 has to be greater than VBE2, correct? Seems reasonable. So that means that transistor Q1 is now carrying more current than transistor Q2, right? So IC1 has to be greater than IC2. We call this current steering, right? We still have the restriction that IC or IEE1, or excuse me, IE1 plus IE2 is equal to IEE, or IC1 plus IC2 is equal to alpha IEE. So we still have that restriction, but what we're observing is that more current is going to flow through our left transistor, which means less current is going to flow through our right transistor. What does that do to our potentials at our output? If IC1 is much larger than IC2, which of our output terminals is at the higher potential? Vout1 or Vout2, which one's going to be higher? Vout2 will be higher, right? What we'll find out in a little bit mathematically, but what we can kind of just understand looking at this guy, right? IC1 is related to the exponential of this guy, right? So it shouldn't take a whole heck of a lot of difference in our, so it shouldn't require our differential voltage to be incredibly positive or anything like that to force all of the current to be effectively carried by IC1 and none of the current to be carried through IC2, right? So we can effectively, if our differential input signal is large enough, we can damn near turn this transistor off, meaning that Vout2 will be all the way up at VCC, and Vout1 will be at VCC minus alpha RC IEE. So we can steer our output voltage across a particular range by shifting current from one side to the other and vice versa. So let's see, how can I write this down? So since that does not look like a good sense, alpha IC1, no, that's not right. way is proportional to the exponential of VBE over VT for VID greater than 0, we should see that V out is going to approach negative RC alpha IEE. Sorry. The book assumes, stop it, alpha RC IEE. Sorry, the book early on just says assume alpha is equal to 1 to make you not have to carry that all the way through, but you'll get a more precise answer if we do it. And it's literally just one simple coefficient. So I'm just trying to remember to continue to do it. All right. Transversely, if we have VN1 significantly less than VN2, what happens? Well, now it's going to be the exact opposite thing, right? Transistor Q2 is going to be carrying almost all of that tail current IEE. So we should see that VID will be less than 0. IC1 will be less than IC2, which is going to cause V out to approach positive alpha RC IEE as that differential voltage gets more and more negative. So we can summarize these results using a couple of pretty simple graphs. So I'll try to do that real quick. So this is what IC1 is going to look like. It's going to be close to IEE, but it's not going to quite get there. IC2 is going to do the opposite thing. So it's going to look like this. It's going to start out really close for negative values of VID. And it's going to get really close to 0, but not quite get there. At exactly 0 differential voltage, we see that both of our currents have a value of alpha IEE over 2. And then for our output voltages, draw some lines here. We're going to have a very similar looking situation. So the top one on the left-hand side is V out 1. Bottom one on the left-hand side is V out 2. At our differential voltage, they're both going to have a value of exactly VCC minus 1/2 alpha RCIEE. And the minimum value for either of the individual output voltages will be VCC minus alpha RC IEE. This is 0, and we are looking again for our individual output voltages as a function of our differential. All right, so this is how we expect things to behave. We haven't introduced a heck of a lot of math. We're just kind of going on our prior experience with how BJTs operate. So with that in mind, now that we have some idea of what's going on, let's look at this guy in a much more mathematically rigorous fashion. So that was our qualitative analysis. Now let's get into some quantitative analysis. So if I have my differential pair, amplifier, V out 1, call this guy Q1, call this guy Q2, V out 2, RC, like so. I'm going to label some currents here. This will be IC1, this will be IC2, this will be IE1, this will be IE2. Got my tail current right here, IEE. And instead of dealing with VN1 and VN2, I'm going to deconstruct my input signal because it's going to make the math easier in the long run. So I'm going to say that 1/2 of my differential input signal is applied at the base of transistor Q1. And the other half of my differential input signal with a negative sign, because I'm subtracting it away, gives me what I have applied at the base of transistor Q2. We'll see shortly that if I do Kirchhoff's voltage law around this loop, I'm just amplifying my differential input signal. Okay. So we know that the common mode signal is entirely rejected, so we can treat that portion as 0 because we know that the amplifier does nothing to it. And so I've simply just deconstructed VN1 and VN2 into positive VID over 2 and negative VID over 2. Our goal here, and it's important to keep this in mind because it's going to take an awful lot of steps, is to determine our differential output voltage VOD and express it as a function of our differential input voltage. So with that in mind, let's just kind of start looking at something, right? We know that V out 1 is going to be equal to VCC, our power supply voltage, which I guess I should label, minus IC1 times RC, and we know that V out 2 is equal to VCC minus IC2 times RC. And from this, our differential output voltage, VOD, is V out 1 minus V out 2, which is going to simplify to negative RC multiplied by IC1 minus IC2. And I'm going to call that delta IC. It's simply the difference of our collector currents. All right. So our output relationship to this point has nothing to do with our input voltages whatsoever. So I'm going to add another step to our goal. Okay, it's going to help us along the way. We need to figure out how to determine delta IC also as a function of our input differential voltage, right? Because once we know what delta IC is as a function of our input differential voltage, we can substitute it in directly to the equation that we just developed, and we're good to go. So let's start working on that. So I'm going to write a KVL equation around this loop. Going from ground to ground. And just so that we're clear here, I have some voltage VBE1 here, and I have some voltage VBE2 here. And I guess actually a better way to draw the path would be like this. So my KVL equation, I'm going to have negative VID over 2 plus VBE1 then I see the negative polarity terminal of VBE2, so minus VBE2, and then I have the positive polarity terminal of negative VID, so this is minus VID over 2 is equal to 0. And rearranging this guy ever so slightly, I get VID is equal to VBE1 minus VBE2. Anybody see anything out of sorts with that relationship? So, because we're dealing with a BJT transistor, we can express VBE as a function of IC, our collector currents, right? So VBE is VT natural log IC over VT. Since I'm looking for VBE1, that's just going to be IC1 over VT. Right? So what I'm using is the following relationship. VBE is equal to VT natural log IC, oh, sorry, over IS. That's why I was getting a confused look, I bet. Which is the inverse of the relationship IC is equal to IS EXP VBE over VT. Right now I'm using this guy. In a minute I'm going to circle back around to that guy actually. And VBE2 I can say is VT natural log IC2 over IS. So what happens when I have a natural log subtracted from another natural log? What can I do to simplify things here? Anybody remember your pre-calculus stuff? So first term is going to be in the numerator, second term is going to be, I'm going to divide it effectively, right? And so what's going to happen is I'm going to have a common factor of VT times the natural log of IC1 over IS times IS over IC2. This gives me VT natural log IC1 over IC2. Now, we have made an assumption here, so let me be very, very explicit about it. this IS and this IS only cancel each other if our transistors are identical, right? Only works if we have near perfect matching between those two transistors. So if we were trying to make a differential pair out of discrete transistors, generally speaking, it's going to work like hot garbage, and we're going to see lots of common mode amplification, which means everything that we're doing here is bad. But if we are designing a system from the semiconductor wafer up, this is a perfect way to go about things. All right. So we have an equation which relates VID to IC1 and IC2. So we are getting somewhere, but it's definitely not relating VID to the difference in IC1 and IC2. If we apply Kirchhoff's current law at this node X, we know that IEE is equal to IE1 plus IE2. And from this guy, we can see that alpha IEE is equal to IC1 plus IC2. Nothing particularly wild there. We've already visited that guy multiple times today. So nothing real wild there, right? So what I'm going to do is I'm going to use this equation, and I'm going to change this guy slightly. So let's revisit this real quick, right? I can say that IC1 over IC2 has to be equal to the exponential of VID over VT, right? Just by dividing both sides by VT and taking the exponential of both sides. That's exactly related to this guy. Nothing too wild or crazy there. And so what this lets me do is say that alpha IEE is equal to IC2 times 1 plus IC1 over IC2, or IC2 multiplied by 1 plus EXP VID over VT. Rearranging ever so slightly, I get IC2 is equal to alpha IEE divided by 1 plus EXP VID over VT, right? I can do a similar set of operations, and I'll find that IC1 is alpha IEE divided by 1 plus the exponential of negative VID over VT. And now I have a means by which to combine these and figure out what the hell delta IC will be in terms of VID. We only have 10 minutes left, Probably enough time. But so we can observe a couple of things from these equations, right? The first of which, if VID is 0, what do both of these go to? Alpha IEE over 2, right? Because e to the 0 is 1. So we have a common denominator of 2. So we see that when VID is equal to 0, our currents exactly divide. When VID is positive, we see that IC1 approaches alpha IEE, and IC2 approaches 0. But here it's very obvious what the relationship is, right? VID over VT, where VT is the thermal voltage at roughly 26 millivolts. Who's got a calculator on hand real quick? What's e to the 4th power? 54.6, all right? And then what's e to the negative 4th power? All right, so take e to the, well, that'll work. All right, so this one was what was this? Let me just approximate things here. E to the 4th. 54.6. This guy over here was 0.02. Right? Okay. This is roughly representative of how much more, sorry, it should be the other way around. For a positive VID. No, I had it right. Shit. Sorry. 54, 0.02. So what I'm trying to get at is we can see that within a couple of thermal voltages, effectively all of the current is either steered from towards one of the transistors or the other, right? So if we were using this guy in digital logic, what that would mean is that we would actually have pretty fast switching speeds, because we can so easily go from one end of the spectrum to the other end of the spectrum, right? So it only takes a couple of thermal voltages worth of differential input voltage to make one transistor carry either all of our tail current or effectively none of our tail current. So that's fairly important. All right, so let's continue the math. So from our previous results, we can see that delta IC1 minus IC2 is going to become negative VID over VT, alpha IEE up here, minus one plus EXP positive VID over VT. So what I'm about to do, this is the hardest math of the day. I'm going to split this exponential up by effectively just introducing another factor of 2 into the denominator. I'm going to factor that out of both the constant 1 and the exponential function. And so what that's going to look like is here I'm going to have EXP times negative VID over 2. When I take that out of 1, I'm left with EXP positive VID over 2, so that when I multiply those two together, it comes out to be 1. 2 VT. And I'm going to have plus ahead of myself. negative VID over 2 VT here. Alpha IEE. And I'm going to do something very similar to this side. I'm going to take out a factor of EXP to the positive VID over 2 VT, which is going to leave me with EXP negative VID over 2 VT plus EXP positive VID over 2 VT. Close that guy off. Alpha IEE. And I now have a common term. All right. So I have common term of alpha IEE divided by EXP of VID over 2 VT plus EXP of negative VID over 2 VT. And this guy is multiplied by 1 over EXP negative VID, no, over 2 VT minus 1 over EXP of positive VID over twice VT. Right. All right, so let's take a look at this guy just real quickly. I can get a common denominator, right? So what I mean by that is if I multiply this guy over here on the left by EXP of VID over 2 VT, I'm going to get EXP times VID over 2 VT divided by 1. Similarly, if I multiply this fraction by this guy over this guy, I'm going to get EXP to the minus VID over 2 VT divided by 1. So I can say then that I'm going to have alpha IEE multiplied by EXP VID over twice VT minus EXP negative VID over twice VT divided by EXP VID over twice VT plus EXP negative VID over twice VT. This odd looking fraction here, based on exponentials, has a name. Anybody know what it is? Hyperbolic tangent. Very close. So we can say that delta IC is alpha IEE of the hyperbolic tangent of our differential input voltage divided by twice our thermal voltage, leading us to the following relationship. VOD, our output differential voltage, negative RC times delta IC gives us negative alpha RC IEE hyperbolic tangent of VID over twice VT. this is the culmination of our large signal analysis, and it is different enough from everything that we've done before that it did deserve, in my opinion, some significant attention. So we can see that as our differential voltage changes, our current, our output voltage is going to wind up swinging from positive alpha RCIE to negative alpha RCIE. So it's going to swing around that 0 point. All right, I actually ran over, so that's enough yammering out of me. On Wednesday, we really have two options. So I guess I'll hold you here for literally 1 minute more, okay? So our two options are, we can talk about the small signal analysis of BJTs, or we can talk about the large signal analysis of MOSFETs. Small signal analysis of BJTs makes sense because we just talked about the large signal, but the large signal analysis of MOSFETs makes sense because we can do all of the small signal analysis on the exact same day, and they're practically identical, except that R pi is equal to infinity in one of the cases. So which way makes the most sense to you? Keep doing large signal stuff, but move to MOSFET, or stick with BJTs and move to small signal? All right, MOSFETs, large signal MOSFET analysis is next then. All right, and then we'll do small signal after we get back from Easter break. All right, you guys have a great rest of your day.